And then I open this academic session in which Kooijman, Pieter Kooijman, but Petrus, will defend his academic thesis called Innovations in Ambient Mass Spectrometry Imaging from Ionization to Detection. Before we start, I would like to welcome the audience here, of course, but also the audience online. We're always happy when there are many people attending. And I would also like to introduce, well, first myself. My name is Nalle de Vries. I'm the pro-rector for this session. But I think it's also wise to introduce the supervisors who are always here but never named. And the supervisor is Professor Heren. He's a professor of molecular imaging at our M4I Institute. And the co-supervisor who is there online is Dr. Ellis, and he's a senior lecturer here, but also the ARC Future Fellow at Wollongong, a famous place in Australia. Now, having said this, I would give the floor to you, Pieter Kooijmans, to give a summary of your work. Please go ahead.
Dank u wel, pro-rector. Ik zal dit lekenpraatje in het Nederlands houden. Dank u alle aanwezigen hier in de zaal, commissie, oppositie, promotoren en ook de mensen thuis voor jullie aanwezigheid en voor de kans om mijn proefschrift hier voor jullie te presenteren. Zoals jullie wellicht gezien hebben, is de titel van mijn proefschrift Innovations in Ambient Mass Spectrometry Imaging. Vertaald naar goed Nederlands, innovaties in beeldvormende massaspectrometrie onder oorspronkelijke condities. Van ionisatie naar detectie. Dat is een hele mond vol. En in deze 15 minuten ga ik een poging wagen om jullie uit te leggen waar dit over gaat en waar die innovaties waar ik over spreek nu om draaien. Om dat te doen zal ik beginnen met een basale uitleg van massaspectrometrie. En wat mij betreft kan je daarbij het beste beginnen bij het begin, namelijk ionisatie. Ionisatie is het geven van een lading, een positieve of een negatieve lading aan een molecuul. Dat kan je doen op verschillende manieren. Je kan iets toevoegen of je kan iets verwijderen. Bijvoorbeeld, je kan een neutraal molecuul, hier in blauw, door een elektronenbundel leiden, waardoor het een elektron verliest en eindigt met een positieve lading. Je kan een adduct toevoegen of verwijderen, waardoor het de lading van het adduct overneemt. Of een speciaal geval daarvan en de meest voorkomende vorm van ionisatie bij massaspectrometrie is het toevoegen of verwijderen van een proton, een geladen waterstofatoom. Zodra je dan eenmaal een geladen molecuul hebt, een ion, dan kan je dingen met die moleculen. Zo kan je die in een elektrisch veld plaatsen. En als je dat dan doet, dan zal je zien dat de negatieve ionen naar de positieve pool bewegen en de positieve ionen naar de negatieve pool bewegen. En neutrale moleculen doen niets. Wat u misschien is opgevallen is dat het negatieve ion vele malen sneller bewoog dan het positieve ion. En dat komt in dit geval omdat het positieve ion veel groter, veel zwaarder is en daardoor langzamer beweegt. Dat is het fundamentele principe dat onder de meeste massaspectrometrie technieken ligt. We bepalen het gewicht van een molecuul op basis van hoe snel het beweegt in een elektrisch veld. Als je dit doet, dan leidt het uiteindelijk tot een massaspectrum. Dat zal ik even uitleggen. Op het massaspectrum ziet u op de horizontale as het gewicht per lading. Zo doen we dat dan, omdat een molecuul meerdere ladingen kan hebben. En als het meerdere ladingen heeft, dan beweegt het sneller. Dan gedraagt het zich in feite alsof het de helft of 3 keer zo licht zou zijn. Op de horizontale as ziet u de massa per lading en op de verticale as de intensiteit daarvan. Dus nu krijg je allerlei pieken waarvan ieder een ionenpopulatie voorstelt en de intensiteit daarvan. Als we dat nog één stap verder doen, dan komen we bij de beeldvormende massaspectrometrie. En dat is iets waar onze groep in Maastricht in specialiseert. Wat we daarbij doen is dat we, als we een materiaal hebben dat we willen analyseren, dan, zoals hier bijvoorbeeld een rattenhersen, als we daarvan de verdeling van moleculen binnen die rattenhersen willen in kaart willen brengen, dan snijden we die door, zodat we een mooi plat oppervlak hebben. En vervolgens gaan we punt voor punt dat oppervlak analyseren, punt voor punt, een spectrum opnemen van alle moleculen aanwezig op dat punt. Dan eindig je dus met een hele grote stapel spectra. Dat ziet u hieronder, rechtsonder. En die hele grote stapel spectra's kan je vervolgens omzetten naar beelden. Dus voor iedere piek in een massaspectrum kunnen wij een beeld produceren. En als we die piek correleren aan een specifiek molecuul, dan kunnen we dus zeggen, oké, dit molecuul heeft deze verdeling binnen dit materiaal, binnen deze hersenen bijvoorbeeld. En waar doen we dit nu voor? Dat is uiteenlopend, maar voor dit proefschrift en voor mijn onderzoek is dat, kan ik dat vrij ambitieus stellen, de complexiteit van de wereld kunnen meten. Dat is een heel breed doel, dus laat me het ietsje specifieker maken. Wij willen bijvoorbeeld mee kunnen kijken met de chirurg terwijl hij aan het opereren is. En informatie kunnen halen terwijl hij aan het opereren is van de moleculen die hij aantreft. We willen de structuur en de complexiteit van planten kunnen analyseren. We willen snappen hoe planten in elkaar zitten en hoe ze werken. We willen bijvoorbeeld doorkrijgen hoe schimmels vechten tegen pesticiden. Dus concluderend, we willen eigenlijk in een droomscenario elk materiaal kunnen meten in zijn oorspronkelijke staat, in zijn oorspronkelijke omgeving, met zoveel mogelijk originele structurele complexiteit en de volledige moleculaire complexiteit. En dat willen we dus doen voor ieder molecuul. Zonder chemische voorkeur, van heel klein tot heel groot, van heel basisch tot heel zuur. En we willen de relatie van ieder molecuul tot zijn omgeving in kaart brengen. En dat is dus waar dit proefschrift begint. Beeldvormende massaspectrometrie onder oorspronkelijke condities. Dus we willen die beelden maken met het materiaal zoveel mogelijk in zijn oorspronkelijke condities. De techniek die wij daarvoor specifiek gekozen hebben, of waar wij op focussen, is laserablatie elektrospray ionisatie. Nog weer een mondvol. Het komt erop neer dat we hierboven een lens hebben. En door die lens schijnen we een infrarood laser op ons monster. In dit geval is het een rattenier. En die plek op die rattenier, die ableren we. Daar verwijderen we materiaal, dat schieten we los. Dat materiaal komt los van het oppervlak en kruist daar vervolgens een nevel van geladen druppeltjes. Een zogenaamde elektrospray. Die nevel van geladen druppeltjes die draagt zijn lading over op de neutrale moleculen die van het oppervlak komen. Daar vormen dan in de lucht vormen daar die ionen. Die worden opgevangen in de massaspectrometer en geanalyseerd. En hier links ziet u dan hoe zo'n spray er in realiteit uitziet. Dit is heel erg klein. Dat is met een microscoop gefilmd. Zo'n soort spray. Dat is op zich heel leuk. Deze techniek bestaat. Deze techniek is op zich zeer bekend. Maar hij heeft zo zijn beperkingen. Zo is het gebaseerd op elektrospray-ionisatie. Elektrospray-ionisatie is de meest gebruikte techniek ter wereld. En voor goede reden, het is heel erg goed. Maar het heeft een paar nadelen. Eén daarvan is dat het vooral geschikt is voor medium-polaire tot hoogpolaire moleculen. Dat laat dus een gat over aan de weinig polaire kant, waar wij graag naartoe zouden willen. Die moleculen zouden we ook willen kunnen analyseren. Dat gat kan worden opgevuld onder andere door plasma-ionisatie. En dat is waar hoofdstuk 3 van mijn proefschrift over gaat. Het maken van een bron, een analyseapparaat, waar we plasma-ionisatie kunnen gebruiken om die beelden te maken van moleculen, van materialen in oorspronkelijke condities. Dus hier ziet u nu een schematische weergave van deze bron. Het is eigenlijk dezelfde weergave als zojuist, alleen hebben we nu aan de linkerkant een argonstroom met een pijl. Dat is een argongas. Die leiden we langs de elektrospraynaald. Maar voordat hij langs de naald komt, leiden we die eerst tussen 2 elektrodes door, die we onder hoogspanning hebben staan. Die hoogspanning zorgt voor elektrische ontladingen, zoals u heeft kunnen zien op de kaft van mijn boekje. En veroorzaken daar een plasma. Die creëren van dat argongas een plasma, dat is een geladen gas. Dat geladen gas stroomt vervolgens gelijk aan die elektrospray waar we het zojuist over hadden, langs de neutrale moleculen die we van het oppervlakte los hebben gehaald, vormt ionen en die worden weer opgevangen in de massaspectrometer voor analyse. Dit is hoe het schematisch eruit ziet. Dit is dus dan uiteindelijk het 3D-model zoals wij die hebben ontworpen hier in Maastricht. En dit is dan hoe het er in de praktijk uitziet. Hier aan de bovenkant, even kijken, ik heb geen... Kunt u dit zien? Ja. Hierboven ziet u de lensbehuizing, dus hier komt de laser naar beneden. Hieronder ziet u het sample, in dit geval een blad. Dit is dan de bron waar, het plasma wordt gecreëerd. En hier is dan de massaspectrometer inlaat. En als je dan van de voorkant kijkt, is dit hoe de elektrische ontladingen in dat plasma eruit zien. Waar doen we dit dan voor? De studie waar we deze bron op gevalideerd hebben, is het analyseren van pesticiden op tomatenbladeren. Zo ziet u hier links een tomatenblad, een foto van een tomatenblad. En de eerste 4 beelden zijn van natuurlijke moleculen die verdeeld zijn binnen het blad. En deze 5e, dit is een pesticide waar we in geïnteresseerd waren. Die waren aangebracht op het tomatenblad. En hier zien we dat die pesticide nog steeds aanwezig is op de plekken waar het is aangebracht. Dat is iets wat we wilden bevestigen. Dit 6e beeld laat hem weer de verdeling zien van antranilonitriel. Dat is een afbraakproduct van deze pesticiden. En we zien dat dat afbraakproduct weliswaar geconcentreerd is rond dezelfde plek waar de pesticide zit, maar dat het zich veel verder verspreidt door het blad heen. En dat is een ander ding dat wij wilden bevestigen met deze metingen. Dus wat hebben we nu gedaan? Wij hebben de mogelijkheden van deze meettechniek verbreed naar andere technieken en naar andere moleculen. En als bijkomend voordeel is deze plasma-ionisatie een stuk robuuster gebleken dan elektrospray-ionisatie, waardoor de beeldkwaliteit ook hoger is. Dat brengt bij hoofdstuk 4, laserablatie van eiwitcomplexen. De analyse van eiwitcomplexen, je kunt bijvoorbeeld denken aan antilichamen, wordt steeds belangrijker in de natuurwetenschappen. En met name de analyse van intacte eiwitcomplexen. En lang is gedacht dat laserablatie van eiwitcomplexen niet geschikt was voor deze analyse. Er werd eigenlijk gedacht dat als jij met een laser eiwitcomplexen ableert, dat je zoveel energie erin stopt, dat je de eiwitten denatureert. Dat de subunits uit elkaar vallen, dat het volledig ontwikkelt en dat je daardoor het eiwit niet meer intact kan meten. Als het ware is het een gekookt ei geworden. Wat blijkt nu? In dit hoofdstuk beschrijven we een methode, met name een oplossing en een aantal condities, waar als je daaraan voldoet, je het eiwit in zijn oorspronkelijke vorm kan houden en volledig gecomplexeerd en nog in zijn oorspronkelijke vorm in de massaspectrometer kan krijgen om daar je analyse te doen. Het eiwit is dus niet gekookt, maar rauw. Dit hebben wij gevalideerd, onder andere op eiwitten als hemoglobine en immunoglobuline G. Dus hier ziet u de piek van hemoglobine, intact hemoglobine. Brengt mij bij hoofdstuk 5, dat is detectie. We kunnen namelijk wel streven voor zoveel mogelijk complexiteit en voor voor alle moleculen willen meten onder alle omstandigheden. Maar dat betekent dat je enorm veel complexiteit introduceert in je spectra. Dus dat betekent dat je enorm goede detectoren nodig hebt om die complexiteit te ontrafelen. Daarvoor zijn we naar Fourier-transform ionen, cyclotronresonantie, massaspectrometrie uitgeweken. Dat is nog een grotere mondvol, FTICR voor kort. Dat is de krachtigste massaspectrometrie techniek ter wereld. en het best in staat om complexe massaspectra uit elkaar te halen. Sorry, een beetje droge mond. Dus nu ga ik proberen u uit te leggen hoe FTICR werkt. Hier ziet u ionen ronddraaien. Deze ionen worden in een sterk magnetisch veld in een cirkelvormige beweging gebracht. Dus die cirkelen rondom deze pijl die je ziet, de Z. En die scheren daarbij langs de detectieplaten, deze grijze platen. Wanneer ze langs die platen scheren, induceren zij een lading. Op het moment dat ze dicht bij een plaat zijn, krijg je een positieve lading. En op het moment dat ze bij de andere plaat zijn, een negatieve lading. Dat zou je kunnen uitdrukken als een sinusoïdale functie. Zoals je hier ziet, vast wel bekend van de middelbare school. Maar als je dit nou niet voor één ion doet, maar voor een tig ionen tegelijkertijd, dan krijg je zoiets als hier. Een heel complex signaal. Dit noemen we een transient. Dit is eigenlijk een samenvoeging van alle sinussen van al die ionen bij elkaar. Vervolgens voeren we daar Fourier-transformatie op uit om van dat complexe signaal een frequentiespectrum te berekenen. Dus dan gaan we van dat complexe signaal naar allemaal pieken die aangeven met wat voor frequentie die ionen ronddraaien. En wat de intensiteit is van die ionenpopulaties die daar ronddraaien. En vervolgens rekenen we dat weer om naar een massa per lading spectrum, oftewel een massaspectrum. Dat is eigenlijk de basis van FTICR. Als je nu zo'n spectrum hebt, zoals hier links, dan zou u misschien denken dat het een heel mooi spectrum is. Mooie, scherpe pieken. Ja, weinig aan te verbeteren, maar als je dan inzoomt, dan krijg je een spectrum zoals hier rechts in het blauwe spectrum. En als je daar de massaresolutie van zou kunnen verhogen, dan zou je zien dat deze ene piek eigenlijk helemaal niet één piek is, maar eigenlijk een samenvoeging van één grote piek en 5 kleine pieken. Met weinig massaresolutie ben je dus blind voor die 5 pieken. En sterker nog, je ionen, de beelden die je zou maken van deze ene piek, zijn een samenvoeging eigenlijk van al deze 6 pieken. Dat houdt dus in dat het beeld dat jij met een lage resolutie zou maken niet klopt. Niet volledig is, plus die andere 5 beelden zie je allemaal niet. Dus je mist heel veel informatie. Wat hebben we gedaan in hoofdstuk 5? Door slimmer om te gaan met het opnemen van de transient, wat handigere Fourier-transformatie toe te passen en ook de omschakeling van de frequentie naar het massaspectrum te verbeteren, kunnen wij deze beelden opnemen in plaats van deze in dezelfde tijd. En daarmee kunnen we dus de complexiteit van onze spectra oplossen.
Ja, meneer Kooijman, u ziet dat ik hem aanzet, want ik
ja,
ga u natuurlijk
ik ben
wel
bij
een
mijn samenvatting, dank u wel.
Oké, want die tijd komt er gewoon bij, hè?
Zeker hebben wij ons moleculair bereik vergroot naar apollaire moleculen, onze eiwitcomplexen overleven infraroodablatie en we hebben ons maximale scheidingsvermogen vergroot. Daarmee wil ik jullie graag danken voor jullie aandacht. Ik hoop dat ik jullie iets heb bijgebracht en wil ik het woord teruggeven aan de prorector.
Ja, dank u wel. Sorry dan dat ik onderbrak. Maar indeed, we have to go to the actual defense of your thesis, and this will be in English. I think you knew about this, yes. At least I hope so. The first question will be asked by the chair of the assessment committee, and that is Professor Honing. He is a professor of analytics for systems imaging at our own university. Professor Honing.
Thank you, Mr. Corrector. Dear candidate, first, before I start to ask you some questions, which is obvious, very much congratulations with finalizing the thesis, working for a long time, and I would say continuously showing your energy to finalize and make this beautiful book truly available. Of course, I have some questions, and I try to start a little bit on just definitions, particularly on page number 13, where you start to speak about the sentence, and I will quickly go to the page where you claim that actually the ionization is highly dependent on the properties of the molecule, and therefore there does not exist something like a, let's say, universal ionization technique. So my first question, maybe that's a trick question, is molecular mass a property or is it just molecular mass?
Highly esteemed opponent, thank you very much for the question, which slightly puzzles me. It's the property. I'd say you could describe it as a property, yes.
Oh, because to help you a little bit, for me, solubility and lipophilicity or dielectrical constants, those are properties, and a mass is just a mass. That's just dependent on the Brute formula. And finally, it's the organization of the Brute formula who defines the properties like solubility. You agree on that?
That is true, yes. Yes, of course.
So then when we speak about small molecules, we truly have a universal ionization technique. And then your statement is not completely right. At least I consider electron ionization as a universal ionization technique for small molecules.
But is it not so that there are small molecules that cannot be ionized by electrospray ionization?
But every molecule has an electron or have electrons. It depends on the energy.
Yes, of course. And I guess there's also not a clear definition of this molecule does not get ionized and the other one does get ionized. It's all on a scale. It's all relative. So if you would have them in a complex mixture, you would have some molecular classes that are more easily ionized than others and therefore overrepresented in your mass spectra. So yes, it's not as black and white as I might have put it. Yes.
That's a little bit where I wanted to go. Maybe and a second small question that's on page number 17, where you actually claim at the top of this page, where you claim that sometimes you don't need such high resolution in ICR. That an orbit trap is sufficient for most of the analytical problems, but you don't say how much is needed for most of the analytical problems. And later on, actually in page 21, you claim in the conclusion that you typically will use ICR to push the boundaries of analytical science to analyze lipids. So I'm a little bit curious now. What's your opinion? Do you like FTICR to do it really high resolution, or is it dependent on what you like on a daily basis instead of an analytical problem?
I'd argue that for most analytical problems, high dynamic range and a good coverage of molecular classes is more crucial and more limiting than mass resolving power. And that for most cases, you would rather sacrifice mass resolving power over sensitivity or dynamic range or speed of analysis.
Then we completely are on the same page. That's good. And then the sentence is within the context, of course. So I would like to take you to page number 58, to table 3.1. A very interesting table. And first of all, I do not completely agree with the annotation of the main ion for cholesterol, because that means that you need to lose a so-called closed shell OH minus out of your molecule just like that. And unfortunately, in my life, I never saw that. Maybe it's new. Maybe you can explain me. But I would argue, no, let's first ask you, why did you annotate it like this?
I think I annotated it like this out of lack of space in the table. I would argue this is the loss of water and the gain of a proton.
Yeah, no, then we are completely on page.
Yes, which in the end, if we argue that mass is just is not a property but just the accumulation of atoms, would calculate to the same thing. But yes. A technique.
But we are analytical chemists, so we want to really do things exactly and nice according to the rules, of course. Another maybe strange remark is I'm doing a long time mass spectrometry and I use molecular masses to start off, but I normally do not use grams per mole. Are you a little bit more organic chemist or are you truly an analytical chemist?
Maybe neither. I'm not sure. I'm supposed to be an analytical chemist. Yeah, in this case, I'd say grams per mole might be a little bit more familiar to most people reading this article that it is based, that it is targeted to.
Professor Honing, are you satisfied? Not entirely, I think.
Not completely, but I will rest my case here.
Okay. Well, thank you for your contribution. So I can turn now to the secretary of this degree committee, and that is Professor Kooi, and she's a professor of medical physics at our university.
Thank you, Mr. Pro-Rector. Dear candidate, also I would like to congratulate you with your excellent thesis, and I also would like to congratulate your promotion team. So I read your thesis with great interest, and I was impressed by the advances that you achieved in MSI. And although my field of research only differs one letter, MRI versus MSI, there are still large differences in these fields. So therefore I have still a few questions for you on MSI. So my first question is on chapter 5, on figure 5.4, on page 98. So I was wondering whether you can inform me what is the spatial resolution of these images and how you can calculate it.
Highly esteemed opponent, thank you for the question and the kind words. I have to admit that indeed in these there is no scale bar.
But I mean, maybe you can just explain how you could calculate.
Sorry, it's 150 micrometers.
Right.
Pixel size.
Yeah, so that's the pixel pixel size. Yeah, but yes. Does that really give you the spatial resolution in the images?
No, it does not. Indeed, you are correct. If features are more blurred and spread out over multiple pixels, then in fact it doesn't resolve. It's not your resolution. That is a long discussion within the MSI field. So yeah, your effective resolution is lower than 150 micrometers.
Yes. And do you have an estimate, like how much lower, or? So what kind of criterion could we use to? Typically,
yeah, I might be, well, I might get critique on this, but we typically do not spend too much time worrying about this. We simply want as high resolution as possible as we can get, and we make do with whatever we can get. I would argue that in this case you're looking at that your resolution is maybe 3-4 times actually the 150 micrometer pixel size.
Yeah. Yeah, I think the Nyquist criterion it would be 2.3 times the pixel size. But if you look at these images, especially, for example, image H, can you see details in this image in the order of the theoretical spatial resolution?
No, absolutely not.
So what is actually the limiting factor then here?
This is signal to noise.
Yes.
Yes.
Yeah.
So in this case, we do not have basically the dynamic range to get a good signal to noise value on these low abundant lipid species.
Yeah. Is there anything you could have done to improve it?
If I could have, I would have. I've spent quite a few weeks on these images. No, this is the best I can do. And the only reason it's in there is because it is a visible peak in the mass spectrum. And it is a species also that we can annotate. But no, the resolution is different, though I might argue that it is, well, I could argue that it has a distinctly different distribution than the main peak in this spectrum.
Right, but I was just wondering, you know, if you, because you have like really small pixels, but if you would like collect the signal of different pixels, couldn't you, you know, improve the SNR in the image?
Well, so for the signal to noise of the whole image of the entire material is already in figure B. So that is the signal to noise that we get if we take the signal over the entire tissue. We could theoretically downsample the quality of the image.
Yes.
And yeah, that might improve a bit of the signal to noise, though I'm always a bit skeptical about, I know it's graphically sometimes more pleasing to do things like downscaling or smoothing or other techniques, and also sometimes more convincing. I personally rather see the raw data as possible. That's my personal preference.
Okay. Yeah, I was wondering if these images, you get nice images, but it would also be interesting to quantify. So, yeah, what would be the possibilities and how could you calculate, you know, absolute concentrations in, you know, millimolar per cube millimeter or something like that?
Yes, this is a big topic of debate within the mass spectrometry imaging field. It's not a part of this thesis, basically because these techniques are relatively in its infancy, and the quantitative studies are mostly done with more developed methods, such as MALDI-MSI. And for those, we have techniques of doing, for instance, internal standards or having homogenates spiked with an internal standard next to the tissue, so you can do a one-to-one comparison and do quantification.
Right. Yeah. So for this is still something that maybe can be developed in the future. Yeah.
Yes, certainly. The techniques exist for other MSI techniques, but for this it fell out of the scope.
Right, so I would like to thank you for time's sake. I would like to give the word back to the prorector. Thank you.
Okay, thank you, Professor Kooi. I now turn to an online opponent, and that is Dr. Anderton. Dr. Anderton is researcher in spatial metabolomics at the Pacific Northwest National Laboratory in the USA. So the floor is yours.
Thank you. Dearest candidate, greetings from the far west. Congratulations on all this great work that you have in this thesis, and the P in PhD you've probably heard is probably really it's perseverance, not philosophy, but you've really shown a lot of perseverance in getting all this work done. So I had a couple questions related to chapter 4 of your thesis. Throughout the rest of your thesis, you have, in the earlier chapters rather, you have some great images off tissue. The work you show in chapter 4 is really cutting edge. One of the things that's, I'm interested in understanding is there's not a lot of, or there's no imaging of proteins off of tissue. And I want to understand what were the key challenges related to doing that kind of analysis.
Esteemed opponent, thank you very much for the question and for the kind words, and thank you for getting up this early. Indeed, chapter 4 does not include any imaging. It is something we have attempted to perform. The difficulty here, I'd say, was mostly due to sensitivity. These were early stage experiments, so we were already happy that we were able to get good mass spectra from solution. From images, from tissue, it's always a bit more complicated. And also, it's unclear at this point how how crucial, how required it is to have your protein in this matrix solution that we describe in this chapter, in order for it to be desorbed within as a complex. In a tissue, obviously, this is much more difficult to achieve.
So on that too, realizing, as you noted, the need for water and using the IR ablation, how much endogenous water do you think you would actually need in order to get some of these protein complexes directly from tissue? And I have a follow-up question to that, which is, especially if you look at figure 1 in chapter 4, you see the native conditions and the denatured conditions. That water content, if you don't have sufficient water content, how would you know whether you're looking at a denatured complex from the lack of endogenous water versus a native complex?
Sorry, could you rephrase that question?
Sure. So I guess the first part is you need the endogenous water in order to ionize or ablate and then ionize these native proteins. Do you have an idea of how much water you would actually need? And I don't know that there's a right answer to this, but do you feel like you would be able to resolve whether if you saw a protein complex, you would know it was in the native or the denatured condition, especially because you have that water balance? And if you don't have enough water, you might still ablate it, but it might have been denatured in the first because you didn't have enough water for the tissue to stay complex, or for the protein to stay complex.
Yes. For the first part, how much water content in tissue? I think so. I'd argue that it's most likely so it's the matrix around the protein complex that protects it from the energy deposited by the laser ablation. So in solution, obviously, that's water or glycol, actually, in this case. I would suspect that tissue has enough matrix to absorb that energy for it not to fully fragment native complexes. Though fragmentation will absolutely occur, as you could already see in our results. We have fragmented some proportion of the native complexes. Whether that's in tissue is enough, it's difficult. Whether it's possible to discern between whether you've denatured, because if I understand correctly, you would like an answer to if it's an experiment to determine if it's denatured on tissue or during the ionization step.
I guess more of a, if you're trying to make a biological interpretation of what you're measuring, how would you know whether something was a native complex or something you just denatured and now you have, different charge states accordingly that you're able to see, as you show in figure 1A and B?
So yeah, okay, that makes it more clear. Yes, so we argue that we are looking at native complexes based on their charge state. The charge state, which is relatively low and equates to a total mass that would equate to a full complex, including all non-covalently bound units. So that part, I would argue, is the same in tissue, except that there you have the added complexity of that you are not 100% sure of what you're looking at. So you're not 100% sure what the complete unfragmented mass would be or should be. Does that?
Yeah, And that's all the questions I have. I see.
Anderton. The next question will be asked by another guest, and also online, and it's Professor Nielen. And Professor Nielen is an emeritus professor of analytical chemistry at Wageningen University and Research. Floor is yours.
Thank you very much, Mr. Pro-Rector. Dear candidate, first of all, I would like to congratulate you with the completion of your thesis, which is really a beautiful booklet, so very well done. And it was also a great pleasure to collaborate in a joint project with you several years ago. I still have some questions to be discussed, and I would like to go back to the figure on page 98, which was already discussed by one of the other examiners. And I assume that you agree with me that when you have an image of the same molecule on the same tissue, provided that you have a reproducibility, that you would expect a similar image. But when I look at this figure, and particularly the subfigures H and I, then in the spectrum, the signal to noise is rather similar. I mean, you responded to one of the previous questions that the signal to noise is important. So according to figure B, the signal to noise is rather identical for substance H and substance I. But substance H and I are identical. They are exactly the same lipid. They have the same physical chemical properties. So the distribution in the tissue should be identical. However, the results in figure H and I show that the distributions are not identical at all. So what's going on here?
Highly esteemed opponent, thank you for the kind words and the question. Yes, indeed, these are biochemically identical, that is true. As it happened, the intensity of figure I is slightly higher, as can be seen in subfigure B. Yes, there is a. It seems to be that figure I has more of a localization in the center than H. But given that how close this is to the noise, I would hesitate to draw too heavy conclusions from this. In general, I'd say the distributions are somewhat similar.
Just to interrupt you shortly. So what would you consider noise in this respect? So what's the origin of the noise?
So the origin of the noise, you ask?
Yeah.
In this case, it would. In this case, most of the noise is not molecules. It would be electrical background noise. Instrumental noise.
So due to electrical background noise, even although the components is more or less in figure B rather similar, it's confusing the image results, basically, right?
Yes, and what adds to this problem is that DESI is not, the desorption of DESI is not 100% identical for every pixel, so that also adds a proportion to the noise, some fluctuations in intensity, and that aggravates the problem.
Yeah, but in this case, it's the same molecule, right? So essentially, only the readout of the data is different.
Well, so it's an isomer. No, sorry, it's not an isomer.
It's not an isomer, it's identical substance, that's my point.
No, it's an isotope.
Yes.
Sorry, yes.
But an isotope, basically, right?
Absolutely.
I mean, from a distribution point of view.
Yes, yes. Chemically, there should be no reason why these distribute differently.
No. So we agree on that, and that's a little bit puzzling. So then I would like to go back with you to chapter 4, which was already discussed a bit by the previous examiner. And your main conclusion is that by using your method, you get a lower average charge state in the end. And well, that would of course be extremely beneficial, and you argue that perhaps you are pointing here to the more native situation. But my question here would be, how did you perform the instrument? I mean, first of all, you dissolve a protein, I guess, in some buffer, and then what happens in the nano ESI situation and in the other situation?
Yes, so for the nano ESI, the protein, so this was a purchased protein standard, was first purified, as described in chapter 4.4. For the lazy signal, it was not purified at all. It was simply dissolved in the matrix solution, as we dubbed it, and ablated.
Okay, so does it mean that does it mean that the protein has been shorter in solution in the lazy experiment than in the nano ESI experiment?
Theoretically, that is possible, but I believe we made these measurements over weeks with solutions that were made earlier. So I argue that there's no significant difference in time in solution between the two. But these results were very consistent over all of the experiments that we did, and given that we made.
So would you agree that the timing, how long a protein is in solution, has a relationship with the charge state you will finally obtain?
To a certain point. At a certain point, it will find an equilibrium. But I would argue that in this case, we're talking about days to weeks. That equilibrium should have been reached.
Okay, fair enough. So, Mr. Pro-Rector,
I can give you another 2 minutes, yeah. Is that sufficient?
Definitely, yes. So I would like to go back to the table on page 58, where you do not obtain any result for isotrionyl, nor with lazy, nor with laser ablation APCI. And can you briefly comment on why no result is obtained from solution here?
Yes, so this, I must confess, is poor experimental design. The problem here is that most solutions that are compatible with infrared laser ablation are water-based, are polar, and isotrionyl is a very apolar molecule by design. It's supposed to. It's designed not to dissolve. It's designed to stick and not to wash away in the rain. That's why they wanted to have it on the surface of tomato plants. So
it would be similar for cholesterol. I would argue that cholesterol would also not be very rapidly dissolved in a polar solvent.
Yes. Also, our explanation why the results of cholesterol were so erratic. Yes.
Okay. Yeah. So so you point to the solubility. Would it be possible that your main problem here is the proton affinity of this compound, which is rather low?
Sorry, could you phrase that again?
So you point the problem to the solubility only, while perhaps the proton affinity would be a cause of the poor detectability as well. The low proton affinity.
It's technically possible, but given the so what we observed during the experiments was that, especially for isotrionyl, we almost always got nothing, absolutely nothing in the spectrum, and now and then there all of a sudden was a burst. So our hypothesis is that we were actually just then analyzing a droplet, like a droplet of isotrionyl, a cluster, and when we exactly hit that cluster, then we get good signal. Then we get ionization. And for all the other shots, we simply were ablating solution, empty solution. And that is the reason why we...
So you did it by co-solvent?
Well, so the problem here was that sorry, I'll quickly answer.
Yeah.
We wanted to use a single methodology for all of the compounds to be able to compare them. Yes.
Okay. And thank you, Professor Nielen. I now turn to Dr. Harings. He's an associate professor of micromolecular physics and technology at our own Faculty of Science and Engineering.
Thank you, Mr. Prorector. Also, congratulations, dear candidate, for a very nice thesis, which I think is a very nice balance between scientific insights, but also technical or engineering aspects, which I truly appreciate. On your starting page, actually in chapter 2, on page 25, you list numerous techniques to study the chemistry and interactions of biomaterial surfaces. On top of that, obviously, structure is important. And on the next page, you mention structure, also orientation. And although you clearly reach out to a material scientist like me, so conventionally I'm looking into plastics, yeah, very different materials, very different texture. And I appreciate also the inclusions of some examples, some PET or ultra-high molecular weight polyethylenes that you have referred to. But somehow I sense that there might be slightly different definition of structure. And my question to you is about structure. So in proteins, for example, we know that it's not only the chemistry. Yeah, at the end, it's also the chemistry that determines the interactions, but also the function of the higher order structures.
Yes.
Yeah, so you have demonstrated that you can analyze protein complexes, but are there any limitations on studying proteins or specifically the higher ordered structures of proteins in terms of their function?
Highly esteemed opponent, thank you for your question. Are there any limitations? Yes, many, especially if we're talking about ambient mass spectrometry imaging, but even for mass spectrometry imaging in general. In terms of size, I do not believe that is the fundamental limitation. Your instrumentation will have to be suited to the size of the molecule that you're looking at. But that is, I think, not the problem. The main challenge, I think, now is being able to image different molecular classes that you are all interested in the same experiment, in order to make those connections, and see how these structures are interacting. Because indeed, that is the entire philosophy behind mass spectrometry imaging, that we do not just want to see what molecules are in this material, we want to know where are they and where are they in relation to the others.
Yeah, so exactly. So how important is the environment?
Extremely.
Extremely important.
Yes.
Yeah. Okay. Then if we make such a link, so very often you use complementary techniques to visualize structures, for example, electron microscopy. And on page, later on, you give the example in chapter 2. I think it's page 38. You have a figure 2.3. And I was wondering, the TEM images speak for itself. And we talk again, like Professor Kooi, about the spatial resolution. How do I read the top images, especially in terms of length scales? So which information do you disclose, and how should I read the top images?
Okay, I have to warn you, this is research that we refer to. This is not my own research. How we should read these? I guess the top two rows are two molecular species with an overlay on the third row. Well, I think for me what's most striking about these images is the variation in relative distribution of the molecules over time, and that they are complementary but changing depending on structure.
So could you maybe help me in aligning the length scale? So if I look to the scale bars, am I looking to the same length scales, or?
I have to verify, but I would assume so. Yes. Right. I'm sorry.
Well, I just want to to make the point. So it would have been helpful to align the length scales. So for me, I was wondering, I can argue with you the distribution of chemicals, that's fully correct, but I was wondering what's the link between the two images if I can't see the length scale. Yes, but
okay.
That's just a note. Then you talk about, if we talk about, I'm having a very quick question, which is the same. Essence, you use lasers to for ablation of molecules from the surface. So could you help me to understand or how to visualize ablation on a molecular scale, and how destructive is it to the sample if we think about simple IR spectroscopy?
Yes.
We need to take it into account.
IR spectroscopy. Especially for us, so this research is mostly focused around infrared laser ablation, which is very different from UV laser ablation. Infrared laser ablation, we have a much lower chance of fragmenting molecules, but it's mostly heating. Heating of OH bonds, mainly found in water, in most samples that we study. That is heating of the water molecules, which causes a rapid expansion and therefore a explosion type of event.
Yeah, maybe yes, no answer. Is it destructive for the sample left behind?
Yes.
Okay, thanks a lot.
I like yes/no questions and answers. So, because I still would give the floor to Professor Ravelli, Professor of Structural Biology at our university, and as I said before, the time taken for the summary will be added to your time now.
So thank you. Thank you, Mr. Prorector, the candidate. Congratulations to you, promoter, co-promoter, family, and friends. We met each other first time in 2015 when your promoter dragged me into the room of the interview, and you presented yourself as a young, long, friendly, thoughtful, serious, positive guy. You're the first wave of the M4I PhD students. That wave is now coming to the end, but not before I still can ask 1 or 2 questions. And my first question will be asked to your paronyms. Could one of them read proposition number 5?
The end-user perspective should be central in early-stage instrument development. This dissertation impact chapter.
Beautiful sentence. It's close to my heart. I could see myself as a potential end user of one of the techniques you described. Right in the introduction, you write, the aim of this thesis is to introduce technical innovations in the field of ambient mass spec. So my question is, do the technological innovations you have introduced to the fields of mass spec include those early stage instruments? And if they do, how did you involve those end users?
Highly esteemed opponent, thank you for your question and your kind words. Yes, so this proposition has found its way into my thesis, partly because it, in my research, it has not always been in the end user perspective has not always been central in early stage instrument development. That is something I have learned, I think I've grown in, and I think that's also why I put it in as a proposition. It's one of the main lessons that I take away from this research. We certainly have tried to do more in later stages. So earlier prototypes, I have to admit, were not always a success. But the later prototype, especially the one in chapter 3, I specifically tailored it so that, for one, it could be fitted to any of the commercial instruments that was sold. So to have a wider impact, developed software so other group members could use it, and not just me. etc.
So it's not a general statement for the general engineer, but you really reflect on yourself.
Well, it is a general statement to general engineering, but it's not a critique to that. It's more a critique to my own learning process and the steps I have taken.
Chapter 4. The chapter 4 has been discussed already here. Native mass spec, looking at native proteins, very close to my heart. You present nice results. The outlook, directly in the abstract in the discussion, it's about high throughput. But I was wondering whether I understood the chapter correctly enough. Isn't there a real fundamental difference how you make your proteins fly, and might there not be a much broader output than just high throughput? Aren't you fundamentally overcoming some limitations of ESI?
I'm sorry, I do not think I follow this question.
You mentioned that in the nano ESI there could be artifacts at the tip of the needle.
Yes.
You mentioned differences. There's 10% methanol in lazy. Is there organic solvent in ESI? There are a couple of differences.
Yes.
Is the ESI itself, the nano ESI, introducing some artifacts, potential artifacts to your proteins that you might not have with the laser assisted ESI?
Yes, so there are a few ways to explain this. Unfortunately, we did not have the instrumentation and the knowledge to dive deeper in this and try to define this. So that's why we put several hypotheses in the chapter on how we could explain this. One of the explanations for this gentler creation would be either that it has that the proteins in lazy have a shorter interaction time with the charged droplets. The other one could be that that they do not have to pass through the nano ESI needle.
You had already finished your sentence?
Yes.
Okay. Doctor, very sorry, then this is it for this moment. Because, Pieter Kooijman, the time appointed for defending your thesis has now passed. And it implies that the degree committee will now withdraw. To discuss the quality of the thesis and also of the defense you just did, I would ask you and your company to await the results of this deliberation in this room, and thereby I adjourn.
Sta ik er nog op? Nou, staat het er niet op.
Pieter Kooijman. The degree committee here present has assessed the quality of your thesis and of the defense you just did. In view of its positive verdict and taking into account previous qualifications, the degree committee has decided to grant you the degree of doctor. Professor Heren, your supervisor, is authorized to confer upon you this academic distinction in accordance with Dutch University custom, so I invite your supervisor to take the floor.
Do you promise to work in accordance with the principles of scientific integrity at all times, to be careful and honest, transparent, independent, and responsible?
I promise.
Then, by the authority vested in us by law and in conformity with the decision of the committee here present, I hereby confer upon you, Petrus Christian Kooijman, the degree of doctor and grant you all the rights attached by custom and law. As evidence of this, I will now present you with the degree certificate signed by the rector, the secretary, and other members of the committee and affixed with the official seal of the university. Zeer geleerde Dr. Kooijman, beste Pieter. Finally, it's done. And I'm glad that I can be the first one to congratulate you with the success of today. It has been more than 7.5 years ago that you started, in February 2015 at M4I. This is an unusually long time, but then again, these are unusual times. You were there at the birth of M4I, the very beginning of us starting the institute with only a few people like your co-promoter, Shane Ellis, there to set up and rebuild labs and offices. And you have done an amazing job in helping us set up the institute. It was a great and exciting time where we were lucky to be awarded a NWO Coast Grant together with Michel Niele, who's here online today and who I would like to thank for his contributions to this project. And Michel, I think you will agree that we both are glad that Pieter is now standing here and defending today. So it's a nice closure of this project together with Wageningen University. You developed novel ambient mass spectrometry imaging technologies. And it was a project that seemed to fit your skills and interests like a glove, as you demonstrated here today very eloquently. You started to work on LASY, which turned out to be a challenging technology, together with Proteado, that went belly up in the meantime. Phasmatech and IDE, you developed several prototypes that allowed us to do innovative research. The ERA lens never saw the light of day, but interestingly, we're still pursuing some of the initial ideas with a twist where your successors are working on. So you even managed to extend the use of LASY for intact protein complexes, and we've heard a lot about that today, with a cover on analysis and sensing. Instrumentation and method development turned out to be really your thing, and in collaboration with SpectroSwiss, you turned the first commercially sold booster into an ultra-resolution DESI-MSI solution and laid the foundation for work that is currently in the lab, still pushing the limits even further. So your work is still impacting our current research, even though you left the institute more than 2 years ago already. You possess one unique character trait, and that is you are a truly collaborative scientist. And that is shown in all aspects of your work, whether it was with the companies that I already mentioned, by your collaborators inside and outside M4I. You always had ideas, contributions, and took initiative to accelerate them towards success. One perfect example of that is your leading role in the organization of OurCon 5 in Doorn. You already started a year before in Pisa with a team of driven young MSI researchers, including your current paranymph, or one of your current paranymphs. And you turned out to be an amazing organizer and managed to put a wonderful program together, which MSI researchers across the globe now still recognize as one of the few truly student-organized meetings. I want to thank you for that and for making all of us look so good and having this impact on the career of many young scientists. I've said it before, but well done indeed. In addition to a passion for instrumentation development and pushing scientific boundaries forward, you and me share another interest. It's bicycling. And I mean not the mechanically powered type, ladies and gentlemen, but the truly human-powered bicycles. You clearly deliver a little bit more on that end than I do. Every time I check my personal stats on Strava in comparison with the people I follow, you often come out on top. And of course I try to improve myself, but unfortunately my shape is not really cooperating. I had the pleasure to go biking with you on an occasion or two, and you must have been holding back a little, as I could relatively easily keep up. On the way back, the wind had turned, and you kept me out of the wind. He's a little bit bigger than I am, so that helped, which allowed me to keep up. It was fun, but also metaphorically how we work together towards the completion of your thesis. It is this type of symbiotic relationship that is needed in a platoon to achieve everybody's optimal performance. The process of getting here today has not always been easy, and you have experienced both head and tailwind. You credited my patience and inspiration, but in the end, it is you, and only you, that completed the whole journey. So, after you finished your experimental work, you and Anna were going on to travel through Africa before completing your thesis. Unfortunately, that was exactly when COVID struck, and you guys and the rest of the world had to change short and long-term plans instantly. Not what you had hoped for. You started writing your manuscript and to investigate what the next step in your career was going to be. This in a time where everything was in flux and a lot of uncertainty engulfed the world. Writing has never been quick for you, as you are a perfectionist and not easily satisfied. And when I said, Pieter, this is a great moment, let's move on to the next chapter, you always found a figure that needed to be better or data that needed to be reanalyzed. So the thesis completion process took a little longer than expected. Interestingly, when you started in February 2015, you hadn't completed your master thesis yet. And it took until November 2015 until you received your diploma. I see a pattern appearing here, ladies and gentlemen. So now you secured a postdoc at Felix already for 2 years in early 2021, where you've expanded your horizon into the world of infrared spectroscopy with one of our famous national facilities. But then coupling that with imaging mass spec, which will undoubtedly result in a unique facility that I hope M4I will continue to collaborate with. You are spreading the word and still find new innovations to pursue. Your dynamic character is always on the lookout for new challenges and new ways to lead and move ahead of the pack. So don't ever lose that, as it will bring you to unknown and exciting places. I'm going to end with an anecdote. So on my way back once to Maastricht by car, driving south on the highway, I noticed a 4x4 with a roof tent driving in front of me. And somehow, before I thought I had to think about you and Anna. To my surprise, when I drive past you, I see you sitting behind the wheel. So I thought, I'll give Pieter a call. So I call you, hands-free of course, to find out that you're on the road to new adventures to the south of the Netherlands. After a short chat, and of course asking you about your thesis timeline as a formality, you turned off to fuel, and I went on to Maastricht, and that sort of was it. But it also shows how we all choose our own path and have fun unexpectedly interacting with others while we explore the world around us. So Pieter, thank you once again for an amazing job in building M4I to what it is today, and congratulations once again with your newly obtained honor. Very well deserved after all the collaborative work you put into this project. And as a matter of course, I would also like to congratulate your parents, extended family, and Anna, who stood by you along the way and are undoubtedly as proud of you as I am right now. Congratulations.
Dear Dr. Kooijman, also on behalf of the Board of Deans and the whole academic community here in Maastricht, I would like to congratulate you with the honor. And of course, also extend that to family and friends. And Anna, I can't see her, but apparently she's important in your life. And of course, to the friends at M4I as well. I won't pretend, and I must confess that I did not understand everything that happened today. But you stood there, and you seemed convincing, and as one of the opponents said, you indeed were the expert. So, and that is also what you sort of communicated to me, that you know what you're talking about, that you did innovative work. And of course there are questions, but as we also concluded, it's the way of science that we get into discussions with each other. So I hope you will continue to do that. I would also like to thank all the opponents for their contributions, and especially also the ones who were very far away from us, although online. So that does not seem to be much of a burden, but then you should take account of the time differences. Also for your co-supervisor Shane, Alice, who is there in the place where much bicycling will go on actually next week, so maybe you should go there.
Love to.
I thank the audience for being here, online or here in the hall. And I will also now explain the procedure of how we now go on before I finish here. Because we want to take a photograph with all the opponents, also the ones on screen behind us. So it implies that we will usher you out. You will go to the reception area. Then we will do some things here. And then we'll come to the reception area as well. And then I'm the first to congratulate the new doctor. But then after that, we have done that, of course, you can do also. But, you know, there's always hierarchy. So by that, I would like to close this session and wish you good afternoon.
Ja, dat zit erop. Ja, ik ben ook te lang. Ik zou het als prof nooit halen. Dat klopt. Hoewel, ik moet zeggen, er rijdt er een van 2 meter in het profpeloton. Dus het kan blijkbaar wel. Ja, dan moet je jezelf uithongeren en zo. Daar heb ik helemaal geen zin in. Hoe oud ben ik? Oh,